phase oracle versus, let's call it an XR oracle. So remember, the classical oracle was this gate. You put in, say, log n inputs, got out f of the input. And this is obviously unusable as a quantum oracle because it's not reversible. So here we have input x, output x, and this one is, well, output is minus 1 to the f of x, x. And we're actually going to see this kind of oracle used again for Grover's algorithm. And the oracle which best corresponds to the classical oracle was what I'll call an XOR oracle, where you put in x, and then you put in an additional bit, let's call it b, and you get a control not here, and you get b plus f of x here, and you get out x here. So what I claimed is, given an XOR oracle, you could turn it into a phase oracle. Yeah?
So I'm a little confused about this function f and its behavior when you don't give it bits, but you give it qubits as input.
Okay.
Because it was defined that it takes log n bits, and then it gives you back a bit,
Right.
classical bits. But now, your x is a quantum state.
Yeah, so the x is log n qubits, and the output is log n qubits.
Right.
Plus an extra qubit here and an extra qubit here.
Yeah, so the XOR oracle makes sense. It's more the phase oracle I'm confused, because you raise minus 1 to this thing that's not necessarily a 0 or a 1.
Oh, it's either a 0 or a 1. So, yeah. So what I should do is, f of x, written as matrix, as our phase oracle written as matrix. Matrix. So we need to write it as a unitary matrix to say what it does. And what it does is plus 1, minus 1, minus 1, plus 1, minus 1, minus 1, minus 1. This is, let's put another, let's make this balanced. And this, of course, is 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. So if you put in a basis state, it applies the minus sign if the basis state is f of x. So input, say 0, 0, 0, plus 0, 1, 0, plus 1, 1, 0, minus 1 to the f of x. What would happen is you would get out, well, 0, 0, 0 was plus 1. So that's 0, 0, 0. 0, 1, 0 was a minus 1. So minus 0, 1, 0. And 1, 1, 0 is all the way down here, I think, and that's a minus 1, 2. No, it's down here. Down. Minus 1, 1, 0. So what the phase oracle does is you put in the superposition of basis states. It applies a minus 1 to each of the basis states in the superposition for which f of x is minus 1, and applies a plus 1 to the ones for which f of x is 0.
So in each of the different states, it's doing the classical version of it.
That's right. Yeah, but it's just this diagonal matrix. Okay, good. So the phase oracle versus the XOR oracle. And now I want to tell you how to use the XOR oracle to get the phase oracle. X. X. And what we're going to do is we're going to put in the state 1 over root 2, 0, minus 1. And that's, of course, minus into this thing. So what happens? Not applied to a minus is equal to minus minus. Because what happens is you apply the not to the first thing, that turns a 0 into a 1 and a 1 to a 0. And that, so a not is the same as a sigma x. X, fare that better. And so this is minus 1 to the f of x minus. And identity applied to a minus is equal to a minus. So if you fix the input to this extra bit to be minus, then what you get is the phase oracle. If you have the, maybe we should call it the bit oracle, because I think that's what other people call it, or the XOR oracle or whatever. And you can also go from here to here in nearly the same way, except you might have to use, it's not quite as easy, but you can get from here to there.